So this is the graph, and these are all the edges that we're going to add in this graph. So for now, let's comment this and let's create the class graph, and in this let's take init, def init. In this we'll pass self and the number of vertices. Now let's initialize self.v, this is equal to v, and self.graph. This is an array of arrays in which we will pass all the edges. Okay, so now let's create function to add edges to this graph. So this is add edges. This will take the source vertex, the destination vertex, d, and the weight of that edge. So self dot graph, and here in this graph we will pass this edge having this information about S, D, and W, or having S, D, or W. So here see, this is the source vertex of that edge, this is the destination vertex, and this is the weight of that edge. And this is how we are adding edges to this graph array. And now let's create Bellman-Ford method, and let's pass source vertex. We're gonna choose a source vertex to start for Bellman-Ford. Now the first thing that we're gonna do inside this method, inside this function, is that we have to initialize all the vertices with infinity. So initially the distance of all the vertex from the source will be infinity, and the size of this array will be equal to v, which is number of vertices. So let's have infinity for each vertex, and the distance of source vertex to itself is obviously 0, so distance 0 is equals to 0. And here we are externally passing the source vertex, so let's take src. Now we have to relax all the edges for n-1 time, right? And n-1 for this example is v-1. So let's relax all the edges for v-1 times. Let's take a for loop for I in range self dot v-1. So we're gonna relax all the edges for v-1. Now we have to do this for all the edges, right? So let's take the edges for u, v, c in self.graph. U, V, C are S, D, and W present in the graph. So here we're gonna apply the Bellman-Ford's algorithm, which says if the distance of u plus cost is less than distance of v, then we can update the distance of v, right? So first we will check it must not be infinity, distance of u must not be infinity, and distance of u plus c if it is smaller than distance v, then update distance v. Distance v equals to distance u plus c. So after the execution of these for loops, we will be having optimal solution, right? Now we're going to check for negative cycles. And how we're going to do that? We know that after the execution of for loops, it is guaranteed that we will be having the shortest distances for each vertex to the source vertex. But even after the execution of these for loops, we're still able to change the distance of any vertex. That means the graph contains negative cycles. So if distance of u is not equal to infinity and distance of u plus c, for any vertex is still smaller than distance v, then the graph contains negative cycles, and then we're gonna print it. Graph contains negative cycle. And then we're gonna return from here without doing further anything. Else we will print that vertex distance from source, and then we will print the solution. Distance from source, and now followed by the result for I in range self dot v, print I, the vertex and its distance from the source, distance I. And here we are checking for negative cycle, and we need to check it for all the vertices, right? So here we need to add this loop. So that's it. So this is the implementation of Bellman-Ford. Now let's take this graph and let's put it here, and let's uncomment it, and now let's call the Bellman-Ford function. So g dot Bellman-Ford, and now let's pass the source vertex. Source vertex is, let's say, 0. So let's save this and let's run this, and this is the solution. These are the distances of all the vertices from the source. 1, 1, 2 is having distance 4, 3 is 3, 4 having 2, 5 is having distance 5.